so I'm going to do it once again, so that once it didn't work, you will see what I'm doing. So you change to the Summer School 2020 notebooks repository that we have in our ACDH GitHub account, and what you then do is just click here on fork, and ask me where to fork to, and I'm now forking this notebooks repository into my own GitHub account, and then I change to Google, search for Google. So, this is the link to the and now I'm clicking on the GitHub tab here in the opening dialog, and you need to give authorization to Colab to access your GitHub account. And then here are all your GitHub repositories. So here, and then you go to Summer School 2020 notebooks, and you see that we have here 2 IPython notebooks, and we're now working on the first one, 10 AM session. And if you click on it, it opens up the server and opens the IPython notebook. And what IPython is, or the Jupyter actually is a possibility to run programming scripts directly from within the browser. There are various kernels for Jupyter. There's a Python kernel, an R kernel, and others more. And we, in our case, and Colab as such, uses the Python kernel. So we are executing Python code in the browser. This is running on Google servers, and they are giving us the free, basically. And such a notebook consists of cells. So when you click in here, this is a cell. And in the cell, you can basically paste Markdown. So that is what I'm pasted in here. So if you double click, you see the raw Markdown that I put in there. Or you can paste code there. And if you double click in there and then Shift Enter, that executes the cell. And the output is then the rendered Markdown in this case. Same goes for this section on how to start the notebook server locally if you prefer that. So, and what we do now in the first code cell here is cloning the GitLab repo where all the files, the ministerial protocol files lie, into your Colab instance so that you can directly access the files. Hopefully all of you have a real GitLab account because it doesn't work with social logins. So if you use Google to create a GitLab account, then this won't work. But if you execute the cell with Shift Enter, then this takes a while now to load, but it asks you for your GitLab username, enter, and then also for your GitLab password. If you enter, it starts cloning this private repository to your Colab account. That takes for a while to run.
Matthias, can you just increase the font size on the thing? Yes. Because
so better. So and this is now finished, and in the cells you can not only so in this Jupyter notebook you can not only directly access execute Python code, but you can also use the shell basically by this exclamation sign here. So we can list the files that are in the summer school 2020, that is where the repo was cloned, dataset episode. So if you execute that cell and you see these files here, then the cloning worked. Yeah. So and in the next cell, we import a few libraries that we use. This is for 3D printing, displaying things, and then down here the requests library for get, post, and so on requests, and the regular expressions that you already heard about in here. If you execute that, it just takes a while. So Renato already introduced you into NLP. So he already told you that there is a big difference between natural text and structured data, and that in the digital humanities, basically we use NLP, namely most of the time named entity recognition, to extract structured data from these natural texts. And what we will start with is using very simple basic regex to do something like that. And then we will later use a library called Spacey, which is an open source library published under MIT license for NLP processing in Python, and run it on some real world DH data, namely also the ministerial protocols. There are also other libraries. So in the Python world, most prominent are Spacey. Then NLTK is the National Language Toolkit, is mostly used for prototyping and teaching. Then there is OpenNLP by the Apache Foundation, and one of the most prominent libraries is Stanford NLP and Stanford Core NLP, which is a Java library, and Stanford is only a Python binding to that Java library. So again, what is natural text and what is structured text? So if we have this German, unfortunately German doesn't see now, sentence, das Austrian Center for Digital Humanities ist ein Institut der Österreichischen Akademie der Wissenschaften. This doesn't mean anything at all for the computer. In return, if you execute that here, which is a Python dictionary, it says here that institutions in this sentence are two institutions: the Austrian Center for Digital Library with the ID 1. It has an acronym, it has a type, and a URI. And the second one is the Austrian Academy of Sciences, acronym, and so on and so forth. And there is then a second entry in the dictionary called relations. And we say there is an institution-institution relation, so between two institutions, with institution A having the ID 2 and institution B having the ID 1. And if we execute that cell, we store this structured data into a variable. We can print that variable in a more structured format. And what you then see in the next cell is that we can directly access things like the name. So we don't have to search the natural sentence, but we can directly access by having these IDs these keys in the dictionary. So we first say, I want everything that is in institutions of the data variable. These are 2. And then I want the first one, this index 0. Gives me the whole object on the Austrian Center for Digital Humanities, and then I say I don't want the whole object, I just want the name. So, and that gives me then the name. And that is basically what we want to do with named entity recognition from So that's local, yeah. So you have to follow my own account. So the local is the camera, and so what we want to sum it up, what we want to do with named entity recognition in this case is using that sentence, here and finding these entities and transferring it into such a structured data object as we have it here. Yes. So, to start with the most simple way how we can do that is with regular expressions. So there was already a session on regular expressions on Monday, if you remember that. Yeah. So we're going to try to extract time spans or years from biography, from the Austrian Biographical Dictionary by using regex. For doing so, we need an XML library in Python so that we can read the original XML file from a Uber biography, namely this Defrega Franz here. So it's in the GitLab repo that you clone. So all you have to do is executing the cell. So the cell loads this with this with statement, loads the file and parses the XMLs. And what you get then is an element tree object that you can then perform XPath and XQuery executions on. You will hear about XPath more tomorrow, but I can show you some basics here. So in this cell here, what we do is reading again the file and then run this XPath on this parsed XML file. And we want the object with Hauptbezeichnungen and extract the text from that, which is the main biography of this guy called Defrega. And yeah, and print. So first of all, we print his name, and then we print the biography that is in the XML file parsing. Okay, so what we want to do is running regular expressions on this file. So we import the regular expressions library into our notebook, and then we run a so-called for loop here. For loop is iterating over a list of objects, basically. So this command here, re find iter, and then in here the regular expression iterates over all findings of this regular expression in the Haupttext variable. And if you remember, we stored here in the Haupttext variable the main biography of Defrega. So if we run that and print the group 0, which is the whole match of the regular expression, then we see that we extracted all the years that are mentioned in this slide. Any questions so far? Please, if you have any questions, just interrupt me and we'll try to solve that.
Does anybody follow to know when bigger problems? I guess there are bigger problems with just getting into the kits.
Okay. Yeah, I think if we haven't gotten if you didn't manage to clone the repo and start the Colab server yet, I would suggest you could just follow the presentation and or look at our website to see the printing of the notebook, and we solve the problems later, and you can always execute the cells later. If there are any problems with that specific cell, I would try to solve that now, but if it's about Colab itself, I think we just do that in the lunch break instead. Yeah, so you already heard about the regular expression. So this regular expression means find me any digits in the text find me any sequence in the text that has between 2 and 4 digits. So that's basically years. And if you look through the text, you will see that there is one time span in there, so this regular expression wouldn't doesn't get the time span, as it's only between 2 and 4 digits. So we have to extend in the next cell the regular expression to also get this time span. And how we do it? There are several ways you can do that, but one of them is creating a so-called group in regex, and a group is a group of signs that you can then use multipliers on. So we say here in the group we want anything that contains digits and dashes, and we want it between 2 and 7 times. And so we get not this 65 in here, but the whole time span 1863 to 1865. Yes. But that is, of course, not what we wanted to do. We didn't want to extract time spans, but named entities. And so we extend our regular expression here. So we start with the original one that finds the time spans and the years. And we then add here, shouldn't do that actually, as it catches everything, but and then we say there is a space, then there is nach, which is in German too, and then there is again a space, and then there is something that we want to catch that has normal characters and also uppercase letters, because places start with uppercase letters in German, so there needs to be an uppercase letter at the beginning and then some other letters. And then we print here the first group that matches. So in the parentheses here, these are so-called groups. So the match, the partial match of the regular expression, if you keep them in parentheses, it stores it in a group. So this is group 1, and the second parenthesis is group 2. And group 0 would be the whole match. So what we do here is printing group 1 and then group 2. So printing group 1 after year, because this is the year that we are matching, and printing group 2 after place. And this gives us, execute the cell. This gives us at least 3 places that the guy traveled to in 1860, 1862, and 1867. So we see that we didn't get all the named entities that are related to time spans with that regular expression, but we got at least 3. Any questions so far? Okay. One problem that we came across when using NLP or named entity recognition on the biographical dictionary, the Austrian biographical dictionary, is the abbreviations, because these named entity or these NLP parsers, they need to do something called sentence splitting. So they split up the whole text that you feed into the system into chunks. First of all, they split it into sentences. And if they don't know the abbreviation in German, so in the Austrian biographical dictionary, there are a lot of abbreviations, then the sentence splitting is done wrong, and this results in wrong parsing. We will see that later. And then the named entity recognition doesn't work correctly. So what we do here is, and Spacey itself does something very similar. We just use regular expressions to split the whole text into sentences. And here's the regular expression highlighted. So what it does is it says, give me all points, exclamation marks, question marks, and colons, and semicolons. And so there is this is a group again. So we say the group with these letter types, and there is only one. And so other than before, where we used this find iter function of the regular expressions module in Python, we use now the split function. That basically means split me the text that I'm feeding into at these matches of the regular expression. So what we get then from that is a list of sentences that we iterate through with this for loop, and we print then the sentence, the ID of the sentence, and the sentence. And if you execute that, you will see that this is by no means correct, because so the first sentence is correct, but the second one already ends with ACAD, as Academy is abbreviated with ACAD. And so he thinks, so this regular expression thinks that this is the end of the sentence, but it isn't. And then there is again the prof, and so on and so forth. So that is one of the problems that we will see even the more sophisticated trained models have. Yeah. So this was a very basic way of extracting named entities. We will now move on to use more sophisticated methods, basically, so Spacey and others. And I want to first show, make a short excursus what a neural network is. Renato already showed it, but I want to only show the very, very basic picture. So basically, a neural network is a network of so-called neurons, and and there are different layers. So in this case, we have a 3-layer neural network, and in every layer, these are the circles in every layer. So every neuron of every layer is connected with every neuron of every layer of the next layer. You see these connections here. And in a neuron, there is a so-called activation function. This is normally a very basic mathematical function that just takes an incoming value, so let's say 0.5, does an operation on it, and passes the outcoming value on to the next layer. So 0.5, let's say 0.2, and then it passes the 1 to the next layer. Yes, so these are, we are passing in values in this first layer in here. The activation function transforms the numbers basically and passes it on to the next layer. And by training the neural network, what we do is not changing the activation function, but we're changing the weights on these relations between the layers. So we know in the end, in the last layer, we want here 0.5, we want here 0.3, and we want here 0.2. This is so for a neural network, you need training data. So what you need to know is, when I feed in these three values, I want it to end with these 3 other values. Does it make sense to you? So you're training it to transform incoming values to other values. That's basically it. Everything that is done with neural networks is doing that. It doesn't matter if it's pixels or IDs of letters, of words, or anything else. It's just transformation of incoming values to outgoing values. So we feed in the first training set data. And so there are no weights on the neural network yet. It comes through, and in the end, there is 0.3, 0.2, and 0.1. We know this is wrong, and what the algorithm now does is transforming these weights here. So the weights are 1 at the beginning, and it's transforming these weights to, let's say, 1.2, 0.3, and so on and so forth, so that the outcoming values are correct to my first training set, to my first training data. And then I move on to the next data point. I feed it in again. There it comes again. It returns again at the end values. They are again wrong. And I adapt the weights of these relations between the layers. And by doing this with millions and millions of examples, the network more and more adapts to return the correct results. And in the end, as Renato also said, we should have evaluation data that then tells us in 0.8, so in 0.8% of the cases, our neural network is producing the correct values. Any questions on this theoretical thing? Okay, so then let's use such a neural network on actual data. We do this by importing the Spacey library, and then we are downloading here with this function the German basic neural network. So this is a German model, and it's exactly trained with on pre-annotated newspaper and Wikipedia articles with exactly that system that I showed you before. It has a lot more neurons and a lot of more sophisticated stuff in between, but the basic function is exactly that. So, and if you have downloaded it, you can load this German Spacey model by using this function into a variable called NLP. And now we put a very simple sentence. Wien ist eine schöne Stadt in Österreich. Die Universität Wien liegt im Schottenring. Heinz Engel ist der Rektor der Universität, into another variable called txt. And the model we loaded into NLP is actually a function called NLP. And now what we do is run our variable, so the text that we stored in the variable, through that NLP function, and store the outcome in the doc variable. The doc variable, what Spacey now does is running the text that we fed it through these neural networks and storing the outcomes in something called a class. And we now use again the for loop. So within the class, it's created something called ends, a parameter called ends. And in ends, it stored all the named entities that it found in the text. So we can run through it and print what it found. So you see here, it found correctly that Wien is a location. It found correctly that Austria is a location. It found correctly that University of Wien is an organization, Schottenring is a location, Heinz Engel is a person, and the university is, again, an organization. So, Spacey comes with a lot of convenience functions like this class here that allows us to visualize the outcome of the operation on the text more user-friendly. We do this with this command here, and you see then the annotation of what we just printed here directly in the text, which is easier to read and control. But Spacey does not only named entity recognition, even if we are now mainly interested in named entity recognition, but also parsing and so on and so forth. And you can also print these called post tags, for example, for all the words in the sentence in here, but we don't want to go into details here. One thing that it also does is parsing, creating a parse tree. Renato mentioned that before in his introductory lecture. This is basically connecting all the words in the sentence to other words they are connected to. And you can also show this as a graph like here. And we don't So to see it on a real world example, I added here some commands that let you download a German newspaper article on Joe Biden, I think. This returns an HTML, so HTML is an XML basically, and we then again from this XML parsing library import a convenience function called HTML that allows you to easily extract text from HTML using XPath, and I'm going to explain the XPath here, but what it does is creating so removing all the links, CSS links, and so on and so forth, and just creating two variables, namely the header of the article, Joe Biden's ACDH-CH, and then the text. So the text is a list of strings, and we just join. So we put this list of strings together with this join command in here, and again feed it into the German model that we just downloaded before, and store the outcome again in a variable called doc. And if you do just rerun the command, this displacing command here that we had before, we see the highlight of the named entities that the system found in this article, and you see there are already some errors in there. So you see, for example, that it didn't get that Biden here is a person, and that important, for example, is no organization. You thought that Amt is a location, and so on and so forth. So there are already errors in there. Important, Hillary Clinton, he thinks is a person, but all in all, the annotation is actually not that bad, so we could work with that. But, so if we use the same model on a biography of the Austrian Biographical Dictionary, so I just printed in the biographical text here, we store it again in this test.txt library variable. If you just print it, you can read the whole biography. And again, we feed this test.txt variable into NLP and store it in doc, as we did already before with the other examples. And if you now render the named entities again, you see that there are a lot of errors in there. So, for example, it thinks that the word is an organization, that Stutt is a location. These are all these abbreviations that I spoke about before. So he always thinks that this is the end of the sentence, so he stops the sentence parsing there. That's why he gets the parse tree that we saw before wrong, and this results in wrong ending. So what you can do to improve this is to, so Spacey uses a dictionary of words that it knows. So a dictionary, so we saw before this neural network, we fed all this text for training purposes through the neural, through a network for training the model. And so it read a lot of words, but it didn't read these special abbreviations that the Austrian Biographical Dictionary uses. So what we can do is add these special abbreviations to the dictionary of words that Spacey knows of. And we do this by putting them here in this list and running through the list and creating a special case for every abbreviation, and then adding it to the tokenizer of the NLP model, so that it knows that this is not the end of a sentence, but it's part of a word. And if we do that and run it through run the text again through the NLP function. We see here, for example, that this helped him to get that Academy is an organization. So you can improve these models with simple orthographical rules that you find in your material. But as we saw before, in this, so these neural networks are trained on newspaper articles and on historical texts. So you will have, in special domains, you will need to do a lot of adaptation to use them. Okay, so now let's do something similar with the ministerial protocols. I'm going to run through it a bit faster, as you already know the basics.
Still faster. I just committed a JSON file with labels for places and stuff. Be committing it now.
Yeah, so we know that the ministerial protocols are stored in TEI, which is XML. So again, we load the LXML library, and we open this one protocol here. It's an arbitrary one. You can just change that to another one if you want to, and run it through the parser. Add the TEI namespace here in a dictionary, and then use XPath to get to the actual protocol. So this is because the actual protocol is stored in a div tag with the type protocol. So we are finding this tag here and storing it in protocol. And now, from now on, we use this protocol variable to run the XPaths on. So the second XPath here in this cell will get you the heading of the meeting by TI head, and then extracting the text that is beneath the TI head element. So this is Protokoll der Sitzung des Ministerrats vom 26. April 1844. 48, sorry. Yes, and so we do that with all, we again use the for loop to get all the agenda items out of the TEI and store them in a dictionary again. And then print it here. So this gives us top 1121, this is the TI ID, I think, if I remember correctly, and then the text that is the transcription of the meeting down beneath it. So if we print now the dictionary, you see in curly brackets, dictionaries are always stored in curly brackets, and you see here the keys and then the values. So by using here, for example, by using calling the agenda item variable where this dictionary is stored in, and calling, let's see, this key here, get the value of that key, and the value of that key items. So so we are asking Python for getting from the agenda items variable the value of the key 2014, which is this transcription of this top number. Yes, and we can use that now again to feed the text through our NLP model. And if we render that, you see here, again, a lot of errors, a lot of things that it didn't get. For example, this Graf Stadion here doesn't get that he's a person, which is actually pretty important in this item, and that is the acting person. And if you don't get that, that would be not so good. If you can see down here that it even thinks that Graphenstadion is location, again here. So this is even worse actually than the named entity recognition we tried on the biographical model. So what you do most of the time with these models is you retrain them. So you take the basic German or English model and you retrain them on your domain material. And how do we do that? So we store a few arbitrary sentences of our protocol up here in another list. So that is now a list of strings. And then we come up with, what Stefan already said, we come up with a list of named entity names here. So we say Stadion is a person, Galizien is a rock, Kreisämter is an organization, Austrian Österreichische Regierung, Austrian government is an organization, Gouverneur is a person again. And this is now a bit of a more sophisticated function. So we use these strings that we created here to create simple regular expressions. So, and we are printing them here. So we are not searching for Graphenstadion itself, but to get also Graphenstadion and all the variations, we add here. So we say here, we search for graph, then there could be a letter, but it doesn't need to be, or several letters. Then there is at least one space, then there is Stadion and maybe again letters. And then we ask him to search for these regular expressions here, and append whatever it finds with the start and end offset in the text in this list. And we append this list then to the train data. Don't need to get the details in here, we just execute the cell. And what we see then is that it creates us a list of tuples with the original text in it, and then a dictionary with an entry called entities, with a key called entities, and in this value of the key, there is a list of entities, and these numbers here are called offsets. So we say from character 0 to character 12, there is an entity called person. And that's what we use as training material for the NLP model. So we have this training data, and then there is actually a pretty simple function in the cell down below that just says, again, loads. Again, load the German model, then create an optimizer, you don't need to know what it is. Then for 20 times, shuffle the data randomly and run, so use the text, this is the text, and the annotations in our train data fin variable, and use that to run it through the NLP update function, which is retraining the model with these new annotations. Yes, and then there has been below in the last line, there is an uncommented function, so that is not executed, it's a comment, but you use that NLP to disk so you can store your model to a local file. We don't need that now because we're just playing around, but if you would really train it, you would store that model obviously for later usage. So if we execute it, this takes a few seconds to run. And we run then, so now it stored the updated model in this NLP variable again, and now we run through the updated model the same text and use this class to render the outcome. And what we see now is that it found at least most of the things that we tried to train. We didn't get that graph is part of graph stadion, but we did get it down here. That is a person. He did get that poor nerve is a person. He did get that Galician is a location, and the Kreisämter and Austrian government are organizations. So obviously, these are far too less examples to really improve the model, but you see already that by running that through, the model is changed and updated. Yes. So that was about identity.